Welcome everyone. Today we're going to look at some of the exceptions to the octet rule. First, let me start by saying that most elements do obey the octet rule, in which they are happy or stable by having 8 electrons in their outer shell or valence shell. However, we're going to look at 3 exceptions. The first category would be exceptions where they have an incomplete octet, where they are happy by having less than 8 electrons. Now, we already know about hydrogen. We know that hydrogen follows what is called the duet rule. Hydrogen only needs 2 electrons to be stable. And that's because it only has 2 electrons, or 1 electron total, and it only needs 1 more to fill in that first energy level, which holds a maximum of 2. Now, beryllium and boron are 2 other elements. They are small elements, and they are also stable by having less than 8 electrons. Beryllium, you will see, has only 2 valence electrons. The Lewis dot structure for beryllium would look something like this. You would just put 2 valence electrons, and you will see that when beryllium makes a molecule, all it needs is to have 4 valence electrons, and with 4, it's happy just by having 4. Boron would be another example. I'm going to demonstrate boron, which has 3 valence electrons, only needs 6 to be happy. Now, they can hold more, but they're stable. Beryllium with 4 and boron with 6. As you know, boron, if you put the 3 valence electrons like that, that would be the Lewis dot structure for boron, and it would make 3 covalent bonds. And as you can see, beryllium makes 2 covalent bonds. So these 2 would be examples of elements that are satisfied by having less than an octet. Now, the opposite to this would be atoms that can have more than 8. And in order for this to happen, these atoms have to be beyond the 3rd period. And technically, the 3rd period can hold up to 18 electrons. Now, most elements do obey the octet rule with 8, but you will see that if you are from the 3rd period and beyond, you have the potential to hold more than 8. So you'll notice that when we're doing Lewis dot electron or Lewis dot structures, you'll see that the extra electrons will always go around the central atom, which would be one of these elements that are in the 3rd period or beyond. 2 very common ones would be sulfur and phosphorus. They tend to be 2 elements that disobey the octet rule. There's one, for example, sulfur hexafluoride. If you were to draw it, and I'm just going to do this quickly, you will see that when you put the 5 or the 6 fluorines here, each line counts as 2. You're going to notice that sulfur has a maximum of 12 electrons around it. The fluorines are obeying the octet rule. It's the sulfur that is the exception. There's another one, phosphorus pentafluoride, and I'm going to just draw this here just to demonstrate that phosphorus in this example is also disobeying the octet rule. You could count the lines. Each line is 2 electrons, and the phosphorus is holding 10, which obviously is more than 8. So these are 2 categories. Either you hold less than 8 or more than 8. Now, there is a 3rd category, which is not as common, and it's an odd electron molecule. And when we say odd, usually the odd number is 7 electrons. One example, and nitrogen is one of those elements that tends to be very common in this category. So if you have nitrous oxide, what happens here is nitrogen, okay, has 5 valence electrons. So look what I'm going to do here. I'm going to put 1, 2, 3, 4. I'm going to put the 5th one over here. That would be a Lewis dot structure for oxygen. I'm sorry, for nitrogen. Then let's do this oxygen over here. It's got 1, 2, 3, 4, 5, 6. What ends up happening here is these 2 will form a bond. These 2 will form a bond. and I'll go ahead and write down what is going to end up happening. You got a double bond there. The result, here's this one down here, and then the one in the middle is the one you see here. Okay? And what I'm going to show you now is let's put the lone pairs or unshared pairs. And you'll notice as I'm writing this, notice that oxygen is not the exception. It has 1, 2, 3, 4, and then each line, this is 5, 6, 7, 8. So oxygen is fine. It's obeying the octet rule. But look at nitrogen. It has 1, 2, then 3, 4, 5, 6, and here is number 7. There's the odd number. And this actually exists. Now, one characteristic about these odd electron molecules is that they are very reactive. Okay? Very, very reactive. So they are going to pretty much react with the first thing they see. And sometimes we refer to these odd electron molecules as free radicals. Okay, and again, the characteristic here is that they are extremely reactive. All right, so let's take a look at some examples. Our first example is beryllium dichloride, and you'll notice beryllium has 2 valence electrons, and chlorine has 7. We have 2 chlorines here, which that would make it 14. 1 beryllium. The total valence electron is 16, or the magic number as we'd like to call it. And we know that beryllium is going to go in the middle. It's the least electronegative element. Watch how I put the chlorines here. And then if we follow the rules, we then connect these two together, and then we give everybody an octet. First, you do the peripheral elements, and then you do the central element. Beryllium would need 4 dots. Now, when you look here and you count, you're going to see we got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Over here, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. We have 4 electrons too many. But if you recall, beryllium doesn't need 8. Beryllium is happy with only 4 valence electrons. So I need to remove 4 dots. And look what I'm going to do. If I remove the 2 down here and the 2 up here, now I'm obeying the total number of electrons. I have a match, and this molecule actually exists like this. Beryllium does not need 8 valence electrons. It's happy by only having 4. So this would actually be the answer to BeCl2. Now, look at this one, BH3. Boron has a total of 6 valence electrons, and hydrogen we know has 1. There are 3 hydrogens here, and only 1 beryllium. So if you look here, our magic number is 9. Hang on, I just realized I put the wrong number here. Let me erase this, I apologize. Beryllium does not have 6. Beryllium has 3 valence electrons. And there's only 1 beryllium. So scrap the 9 there. When I had written the total number, it has 6. Okay, so make sure I was thinking total electrons here. So valence, it has 3. Now the magic number is 6, and we know beryllium's going to go in the middle. Put the H's in the periphery. The next thing you're going to do is connect them. Now, there's nothing to do with the hydrogens. The hydrogens are happy the way they are. So don't add any dots. Now beryllium, if you add 2 dots to give it an octet, and then you count, you'll notice that you got 2 over here, 4, 6, 7, 8. And that's 2 too many. So what we're going to do is we're going to remove 2 dots to make it 6. And we're going to remove them from beryllium. And what ends up happening is that beryllium is happy by having only these 6 valence electrons instead of the 8. So this would be the actual Lewis dot structure for BH3. Now let's take a look at phosphorus pentafluoride. So we know phosphorus has 5 valence, fluorine has 7. So let's find our total number here. So 7 times 5, we got 35, plus the 5 for phosphorus. Our magic number is 40. And here's what we're going to do. We're going to put the P here. We're going to put the F's, just surround it like this. And then the next thing you do is you bond everyone to the central atom. And then we're going to give everybody an octet. Remember, you always start with the peripheral elements. I need to add 6 dots to each fluorine because remember, it already has 2 from the line, which is the covalent bond. So I'm giving every fluorine 6 dots. Now, when you count this up, you got, let's take a look at this one on the top here. You got 1, 2, 3, 4, 5, 6, and then the line is 7, 8. Okay, that's 8. Then you do the same thing over here. That's 16. This one would be 24. This will be 32. And this one over here would be 40. So notice that when I drew this, it matches. Okay, let me erase these arrows to avoid confusion. But right now, it matches. I don't have any space to add any more electrons to phosphorus. It already has 8. In fact, it has more than 8. But what I drew matches the original number here. So despite the fact that phosphorus is holding more than 8, it's actually holding 10 valence electrons represented by the 5 sticks here. Each stick is 2. We can see that phosphorus is acting as an exception to the octet rule. So this would be the actual drawing for PF5. Now let's look at xenon tetrafluoride. So first of all, notice there's a noble gas here. This is not a natural compound. Whenever you see a noble gas involved, it's probably a man-made compound. It was probably forced to react. You don't see this naturally. And xenon has 8 valence electrons. There's 1 xenon. Fluorine, as we just saw, has 7 valence. This one has 4. So when you multiply, you got your 28 valence from fluorine, and then you got your 8 from xenon. So we have here, let me see here, 36 is our magic number, our total. So we're going to put xenon in the middle, and then I'm just going to put the F's right here in the periphery. And then the next thing is connect everybody here. And then give everybody an octet. So we're going to give fluorine 6 dots. Each fluorine will get 6 dots. Okay? And then when you look at xenon, xenon already has an octet. It has 2 here, 4, 6, 8. Now let's count everything up. Now if you look at this fluorine up here, you got 6 dots and a line. That's 8. You got 16 down here, 24, and you got 32. So right now, if you notice, we're short. We're supposed to have 36, yet we only have 32. So I want you to make note of this. This is what happens when you're short. When you're short, the rule is you're going to add electrons, and you're always going to add them to the central atom. In fact, xenon is beyond period 3, so xenon can hold up to 18. Now, how many dots are we going to add? Well, we're at 32. We need to get to 36. So we're going to need to add 4 dots. And you're always going to add it to the central atom. So when you add them in pairs. So I'm going to put 1, 2 here, and then 3, 4 over here. And there are the 4 dots that I just added. And if you look at this carefully, xenon is acting as an exception. It is happy not by having 8, but in this case, it has 12 electrons around it. Okay? So this is xenon tetrafluoride. Now let's take a look over here. We got NO2. So we're going to put nitrogen is 5 valence times 1. And then oxygen is 6 valence times 2. Okay? And then we're going to go ahead. We're going to add this up here. So 12. You'll notice here when you add these, we got 17. Notice this is an odd number. Okay, so this will probably be one of our exceptions under that last category, which is the odd electron pair category. So put the least electronegative element in the middle, put your oxygens, connect them, give everybody an octet, just like this. Okay, and now nitrogen also needs an octet, so we're going to go 2 here and 2 here. We already have 2 here and 2 here with the lines. So everybody has an octet, so we're going to count. And when we count, we got 1, 2, 3, 4, 5, 6, 7, 8 is the line. 9, 10, 11, 12, 13, 14 is the line. 15, 16, 17, 18, 19, 20. So look at this. Here, not only do we have to take away 3, we're going to probably have to do a double bond. Why don't we take out 2 first? Let's go from 20 to 18. And what I'm going to do is, and remember the concept of resonance, we're going to remove, we'll remove one. I'll just take it from the top, make it easier. It could be the top or the bottom, and I'm going to use the left side here. So I'm going to remove 2 electrons. So here we go. I'm going to erase this one. I'm going to erase this one. And then the 2 that remain will double bond. Okay? And as they double bond, we now are at 18. Now, this would be represented like this. We would have a double bond here, and we would have this like that. We still have 2 dots here. We have a single bond on this side. And we still got to remove one more. Now, when nitrogen's involved, what I would do is I would remove the dot from the nitrogen. So what I'm going to do is I'm going to remove one of the dots from the nitrogen down here. So I'm going to erase it. And by doing that, it now matches. We now have 17. So notice that the odd number is where the nitrogen is. And that actually exists. Now, keep in mind, this is also an example of resonance. Because somebody could have said, what about if I want to remove the dots from the nitrogen and oxygen on the right side? And you could do that as well. It would look like this. The double bond would be on this side. You'd have your 2 dots over here, your 2 dots over here, your individual dot here. The single bond would be on the left. And this would be, remember, the double arrow means resonance. And this is what it would look like. Okay? So that would be another option if it's NO2. The exception here is the fact that nitrogen has an odd number, and that is under the 3rd category. Okay? Now let's take a look at, we have triiodide ion. So what we're going to do here is we have iodine. It has 7 valence electrons, and we have 3 of them. You know what? I just noticed that we have a typo here. Hang on one second. So let's fix this. This is a mistake. It should be I3 with a negative here. So that was written incorrectly. It should be I3 negative 1. And so let's fix that here right off the bat. And the magic number here, if you'll notice, 7 times 3 is 21. But remember, when there's a charge, you do an adjustment. When it's negative, you have to add. In this case, we're going to add 1 electron. So we're going to add the 1 electron, so the actual magic number will be 22. Now here, you have 3 iodines, so I'll do it at the bottom here. So you got 1, 2, and we got 3. And we're going to connect them to each other. We're going to give every iodine an octet, just like this. Whoops, let me not do that first. Always do it to the peripheral. Now we go back and do the middle atom. Okay? If you look carefully, I've given every iodine 8 valence. So let's do a count. We want to see if it ends up looking like that. Okay, if it has 22. So we're going to count 1, 2, 3, 4, 5, 6, then 7, 8 over here. 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. Notice we have 20, but it needs to be 22. So again, whenever you're short, you will always add the extra electrons to the central atom. Now look what I'm going to do to make this, to space it out. I'm going to move these two to the side here. Okay, you could do this at the top or at the bottom, and I'm going to add the extra 2. So you got the 2 that were already there. Here are the 2 extra that I just added. Notice I placed it in the central atom so that it matches. That's what you always do when you're short. Now, because this is a polyatomic, because it has a charge, you're supposed to put this in a bracket. Let me move this. Let me move this out of the way here for you guys. And remember, the magic number is 2. Let's put a bracket, and the charge goes on the top right-hand corner. And that's what you do every time that you have a polyatomic. Put it in a bracket and put the charge on the top right-hand corner. Okay? So I apologize for the typo here, but the triiodide ion is I3, and it has a -1 charge.